online platform.
Sir, can you send Jamboard again? I have not got.
Yes, I'll share, no problem. Okay. So if you join this meeting, then using the same, you will able to join this Jamboard. Okay, so I have again shared it. Okay, so I hope you can join it and you can view it.
Good morning, sir.
Good morning. Okay. So good morning, all of you. I'm Dr. Narendrakumar Dasre. Okay, I'll be teaching you engineering mathematics 3 and 4. So in the yesterday's meeting, we have seen that what are the topics in SEM 3 and SEM 4. So in SEM 3, we have part of linear algebra, we have transforms, we have complex analysis, we have Fourier series, and then we have random variables and some statistical techniques. Okay, so each one of this is going to be very useful to you, and that's why we have selected the topics, selected the subjects, okay, according to the future need. Okay, so some of you will go for data science, some of you will go for machine learning, some of you will go for AI. Okay, so what is the mathematics required there, and what you need to understand, according to that your syllabus is designed. Okay, one of my specialization, as I told yesterday also, that mathematics for machine learning, that is my specialization, and again Python programming. Okay, so this mathematics is highly required to you, okay, for the different purposes, okay, in your specialization, and that's why we will be studying this. So first, if I consider the part of linear algebra, okay, then this linear algebra is very useful in data science, okay, to understand the data, to reduce the dimensions of the data, okay, because you will have a huge data. Okay, so how to find the important components in that data, okay, or how to find what is important in that data, and that's why we need to understand this linear algebra. Okay, because linear algebra helps us to know, and that is called, in technical language, we call it as principal component analysis, okay, or more famous with the name PCA. Okay, so this PCA technique, so basic is in linear algebra, and that's why we need to understand the linear algebra. Then we need to understand a signal, whether it is a continuous signal or whether it is a discrete signal. So one question comes in mind, that what an IT engineer has to do with the signal. Okay, but for electronics engineer, it is an electrical signal. For electricity engineer, it is maybe some another signal. For us, for IT engineers, for computer engineers, or for a data science person, it is a trained which moves. Okay, so though technically we call it as signal, mathematically we call it as function. Okay, and in applied language we call it as a trained. So what trained is going in every field in this data, or what the trained this data shows. Okay, so that's why we need to understand this transforms, to analyze that trained, to get the more idea about the trained. Okay, so that's what we have to do. And now if I want to find out the another trained, okay, what will be, or I want to predict something, then I need to understand the statistical techniques and the complex analysis. Okay, and now sometimes the things are unpredictable. Okay, so what are the chances that we will predict in a proper way? So these things which are uncertain, unpredictable, we call them as a random variable. So mathematically we call them as a random variable, and that's what we are going to study, the random variables also. So in this semester 3, we are going to understand the linear algebra, we are going to understand the transforms for understanding the behavior of the signal, behavior of the trained, what is the shown by data, or what the trend is existing, and we are able to guess. And now to predict, we use the complex analysis. And then if I want to go for the each component of this signal or each component of this trend, then we go with the Fourier series analysis to understand the component. Okay, and then we can extend this Fourier series to the Fourier transform, which gives the energy, the main thing of the signal or the trend, that what we do. And then we need the tool called Fourier and Fourier series or Fourier transform, which extends to the Fourier transform. But sometimes the signal, the trend is not continuous. It is fluctuating, it is changing. And so we discretize it, and then we need another tool called Z transform. So in transforms, we will be learning the Laplace transform for the continuous trend or the signal, and the Z transform for the discrete or the stem signal. Okay. And now we'll try to understand the uncertainty by using random variables, and then we'll try to model the situation. Okay, so what is the model this data shows, or what the data speaks? Okay, what is the trend? Can we predict the trend, okay, in this given data? And that for that we need the statistical techniques that we are going to see. Okay, so these are some of the things or the tools that I am going to equip you with these tools. So these tools you can use in the subjects. So you will be studying like data science, you will be studying machine learning, you will be studying artificial intelligence, you will be studying, and these all tools you will need there. Okay, so that's why if you want to get that subjects properly, then you must study these tools properly. So if you understand here, definitely you are going to do better in those subjects. Okay, so this is the base, this is the basic of that subjects, and that's why we'll go with one by one. Okay, so first we'll try to understand the principal component analysis, okay, but in a mathematical way, and that you can extend to the another dimension, or how to reduce the dimensions of the data, that you will able to see. Okay, so I hope you are able to see this.
Sir, I am
Yeah.
not able to join the Jamboard.
Okay,
It's denying the
okay,
access.
okay, no problem if you are not able to join. Okay, I will be sharing here so you can see.
Okay,
Okay.
thank you, sir. Thank you, sir.
Thank you, sir. Yes. Okay, so basically in SEM3, what we are going to do, okay, the examination pattern, all of you know. So we'll have 3 theory lectures, 1 tutorial lecture. So your IA1 will be of 20 marks, IA2 will be of 20 marks, and then average we'll be considering for IA1 and IA2, that will be of 20 marks. Then you will have the mid-sem examination, which will be of 20 marks, and the end-sem examination, which will be of 60 marks. So total this subject will be for 100 marks and 4 credits. Okay, so when will this will be converted into credit, it will be the 4 credit. Okay, now we need this course, okay, to understand the data science, to understand the trends, to understand how we are going to get into the machine learning and artificial intelligence and related fields. So what will be the course outcomes, okay, what you will able to gain in this course. So here we'll start with the matrices, so which is a part of linear algebra. Okay, so the bigger picture is linear algebra, and especially we are going to understand the eigenvalues and eigenvectors. So mathematically, when we say eigenvalues and eigenvectors, technically they are the principal components and the direction of the principal component in which that particular component is acting or is having the effect. Okay, so these are eigenvalues and eigenvectors. Then to understand the trend, we use a Laplace transform. So if it is continuous and if it is a discrete, then we use Z transform. So that we are going to understand. And then if we want to express the given function, the given trend, we need to analyze component wise. Then we use the Fourier series, okay, which expresses the given function in terms of sine and cosine with the different frequencies. Okay, so it analyzes the each component, each frequency of that particular signal, that particular trend. Then we'll understand the random variables, the probability distributions of random variables, and then we will model the situation, and we'll try to understand how good our model is. So if we want to test how good our model is, then we need to understand the correlation, and if we want to build a model for the situation, then we need to understand the regression. So when we'll understand the regression, then we will able to model the situation, and how good that model is, that is decided by the correlation. Okay, so these are the course outcomes. These will be the outcomes when you will understand, or when we will go through this course. Okay, so in linear algebra, we have eigenvalue, eigenvectors, and related topics. In transforms, we have Laplace transform and Z transform. Then in complex analysis, we'll try to understand the differentiation, the complex differentiation, that we'll try to understand. And in Fourier series, we'll express this given function or the given signal in the different intervals, and then we'll see what is the effect of these different intervals on this Fourier series. In random variable, we'll try to understand the variable discrete and continuous both, and then we'll understand their parameters like expectation, variance, then probability mass function, probability density function, and the distributions of these random variables. So we'll go with the standard distributions like binomial distribution, Poisson distribution, and normal distribution. And then statistical techniques. So here we'll go with the correlation and regression. So regression will give us a model, and correlation will decide how good that model is. So reference books you can write down. So these are the books which you can refer. So Advanced Engineering Mathematics by H.K. Das, it's a S. Chan publication. Then Fundamentals of Mathematical Statistics, this is again by S. Chan publication. The authors are Gupta and Kapoor. And then we have one Higher Engineering Mathematics by Khanna publication. The author is Dr. B.S. Grewal. Okay, and apart from this, you can again refer the several books for detailed topics. Like for complex variable, you can refer the book by B.S. Taggi, and then for again advanced engineering mathematics, you can refer by Arvind Kreszik. Then for elementary linear algebra, you can refer the book by Anton and Rose. Okay, so these are the standard books, okay, which you can refer, and have more examples in each of this topic. Okay, so do you have any doubt up to yet? Do you have any doubt up to yet? No.
No, sir.
Okay. Okay,
sir.
that's great. Yes, good. Okay. Now, please, if you have any doubt, then you can stop me and ask your doubt. So don't worry. Okay. And if I ask something, please do reply. Thank you. Okay. So now we'll start with the first topic. Okay, linear algebra. Okay. So linear algebra is related to the matrices. Okay. So basically, we need to understand how this matrix comes into picture. Okay, so let us try to understand this. Okay, so I hope all of you are able to see the Jamboard now.
Yes, sir.
Yes. Okay, so that's great. Yeah. Okay, so first we need to understand linear algebra. And particularly, we are going with matrix theory. Okay, so first we need to understand what is a matrix. So, can you tell me what is a matrix? Any one of you, can you define what is going to be the matrix? So you can unmute yourself and then you can say what do you feel what is going to be the matrix?
Arrangement of two numbers in rows and columns.
Yes, good. Arrangement of the elements in rows and columns. Can you specify how many elements you will have, or can you choose randomly elements? So this is good. We will try to improve this definition.
Sir, the elements can be real as well as complex numbers.
Good. Okay. So elements can be real as well as the complex number. Good. Okay. So how many elements we can have?
How much we need, like infinite?
N number of elements.
N number of elements. So can I have 5 elements? Is there any
Sir,
relation?
I think
Yes,
it
Meenal?
should be in M cross N form.
What is M and what is N?
That can be real numbers.
No, but
Rows
what
For
is
example,
columns.
5 cross.
Rows
M
and
would be
columns.
the number of rows and columns.
Yes. So we have M rows and N columns. Okay. So what we need to understand is when we think of an arrangement, then we must specify how many rows we have and how many columns we have. So if we have M rows and N columns, okay, then how many elements we will have? M cross N. Okay. So now let us redefine the matrix. So what is a matrix? Matrix is an arrangement of M cross N elements into M rows and N columns. Okay, so that is the correct one we can have. So we have the correct definition as, okay, so we have an arrangement of Mn elements in M rows and N columns. Okay, so what we have? We have the arrangement of Mn elements in M rows and N columns. Okay. It is M rows and N columns. Okay, then we call this as M cross N matrix. Okay, so the matrix is denoted by capital letters A, B, and so on. Okay, and the elements are denoted by small letters. So we have, okay, what we'll be having? So we have this matrix A is equal to, okay, we have Aij. So where I is running from 1 to up to M, because we have M rows, and J is running from 1 to up to N, because we have N columns. Okay, so we also write this as A is M cross N matrix, and then we have this AI chain. Okay, I is running from 1 to N, and J is running from 1 to M. Okay, so are you able to get this matrix notation?
Yes, sir.
Are you able to get this matrix notation?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, that's good. Okay, so we got now the matrix, right? Okay, so we will be restricting ourselves to a square matrix. So can any of you tell me what is a square matrix?
The number of rows and columns.
Equal
are the
number.
same.
Equal number of rows and columns.
Absolutely correct. So this matrix has the equal number of rows and columns. Okay, so a matrix with equal number of rows and columns. Okay, so the matrix with equal number of rows and columns. Okay, so that is if A is a square matrix, then we have the standard notation M is equal to N. We use M for the rows and N for the columns. So that is what do you have here? We have number of rows equal to number of columns. Okay, so we have the number of rows equal to number of columns, right? So for example, we can have A is a 3 by 3 matrix, and we have the element A, B, C, D, E, F, G, H, I. Okay, so these are the elements. Or you can have another matrix B, 3 by 3 we choose, and so we can have this is 1 0 0, simplest matrix 0 1 0 0 0 1. Is it a square matrix? Is B square matrix?
Yes.
Yes. Okay, so can I say that B is a scalar matrix? Is B a scalar matrix?
Yes, sir.
Yes, sir.
Yes. Why we can say that this is a scalar matrix?
Diagonal elements are same.
Diagonal elements are equal.
Correct. Absolutely correct. So diagonal elements are equal. Can I say that this is a unity matrix?
Yes, sir.
Yes.
Yes, sir.
Yes, sir. Yes, sir.
So we got
sir.
4 concepts here. This is a diagonal matrix, this is a scalar matrix, this is a unity matrix, and moreover all the elements this is unity matrix because all the elements are the diagonal elements are 1. Okay, moreover, can I say this is upper triangular matrix? Can I say this is upper triangular matrix?
Yes, sir. As
Yes,
well as
sir.
lower triangular.
Lower
Yes,
triangular.
yes, obviously it is a lower triangular matrix also, it is a upper triangular matrix also. Okay, so these are the concepts. So triangular matrix, the another concept we got. And if this is an identity matrix, then we denote it by I, or the order if I want to say, then it is going to be I3. Okay, so we'll restrict ourselves now to the square matrix, and moreover we'll be studying up to the matrix of order 3 by 3. So we'll be studying the matrices of order 2 by 2. Okay, 2 0 4 3. Okay, this is a matrix which is with the 2 rows and 2 columns. This is again a square matrix. Okay, so we'll be studying 2 by 2 and 3 by 3 matrices. That idea can be extended to the n cross n matrix using the programming, and that's what our job is, or that's what we do. Okay, so we understand the concept for smaller things, and then we apply this concept for the bigger ones. Okay, so here we'll do the experiments with this kind of matrices, and then we'll do the programming, and then after doing programming we'll apply this this theory to the matrices with 1000 by 1000 dimension, or maybe 5000 by 5000 dimension. Okay, and that's why using the techniques that we'll learn in this topic will reduce the principal components, or will try to find out what are the important components. And now we'll see the technique how to find the important components. Okay, so now if I want to understand eigenvalue, eigenvectors, okay, so we need to know some certain things. Okay, so again, the important concept I need to understand is determinant. So you have defined the matrix now. So can any one of you define what is going to be the determinant? Can any one of you tell me what is going to be the determinant?
For unity matrix, it's 1.
Okay, for unity matrix it is 1. Okay, so you are talking about the value of the determinant is going to be 1. Okay, but I want to define the determinant. I want to know only what is the determinant. How
The solution of determinant. Like,
yes,
the solution of determinant matrix is called as determinant.
no, matrix is not called determinant. Matrix is the another
It's
concept.
solution. It's solution.
Solution matrix is not a question that we will have the solution.
Sir, I think it's the scalar value of the entries in the matrix.
But can you say, suppose I have a 2 by 3 matrix, so can you find the determinant?
No, so the entries have to be like m cross m.
Like it should be a square matrix.
Yeah.
Yeah, this is very important condition. Don't use matrix. Okay, so first of all, number of rows should be equal to number of columns. Okay, because we have rows in columns in the determinant also. Okay, so we should have the same number of rows and columns. And now try to define what is the determinant. What is the determinant? You have already studied it. Okay, so you know, but we need to write in the proper words. So the most important thing you got, the number of rows should be equal to number of columns. Then only we can have the determinant. Okay, so what else you think? How we are able to define the determinant?
The scalar value of a square matrix.
No, don't take matrix into account.
This
Okay,
is of a
so the concept is something different. So we don't have to consider the matrix into the determinant. We don't need matrix to find determinant. Okay, I'll show you something, and then you try to define. Okay, so I have that. Okay, so here I am not considering any matrix. and I know that this is the determinant and this is the value. Do you agree with me that this is determinant and this is the value?
Yes, sir.
Yes.
Yes,
So
sir.
now we need to define this thing. How to define this?
So, sir, do we go as the modulus of the elements
Modulus
which are
of the elements. Modulus itself has a different meaning.
okay? Okay.
So when we say modulus of minus a, it's going to be a. So we call this as modulus, or we call it as absolute value. So determinant is not the absolute value. So determinant can be positive, negative, zero also. So we cannot say that it is going to be the modulus.
Okay, sir.
Yeah. So basically, we need to understand that there are number of rows equal to number of columns. This is a very important condition. Then this is the scalar value, but not of the matrix. So we don't have to relate the matrix to this. Okay. So we can say the value of an arrangement of n square elements, because here you have rows and columns in as going to be same, no? So in matrix you have mn elements. So here you will be having n square elements. So the value of an arrangement of n square elements in n rows and n columns. Okay. So we don't need to relate this to matrix, because when we say matrix, then it becomes the order of the matrix can be anything, and then we cannot find the determinant for every matrix. Okay, so we have to be careful. So we got the determinant now, we got the matrix now, and now we are ready to go for our actual concept. Okay, so if we want to go for the next concept, okay, then we want the determinant and the matrices both. Okay, so the first thing that we'll define is characteristic polynomial. Okay, so when we say polynomial, that means there are more than one terms. Okay, so we need to understand the characteristic polynomial. Okay, so what is characteristic polynomial is, so I can say let, okay, A be a square matrix. Then the characteristic polynomial, then characteristic polynomial of A is defined as so we need to understand this is going to be the determinant. So it is determinant A minus lambda I. Okay, so we are familiar with this notation. This is lambda. Yeah, we call it as lambda. Okay, so this is lambda. Okay, this is going to be small lambda, this is capital lambda. Okay, so we are using here small lambda. Okay, so now if I consider the determinant of A minus lambda I, because A is going to be a square matrix and I is always a square matrix, so I is this, having the same order as A, and that's why this matrix operation is possible, and then whatever the resultant matrix I will be having A minus lambda I. Okay, so I am considering the determinant of this, and then whatever the equation I will be getting, that equation, or sorry, that polynomial I will be having, and this polynomial is called as the characteristic polynomial. Okay, so now we need to understand the next concept called characteristic equation. So we have characteristic equation. So please be careful. We have to understand the difference between the characteristic polynomial and the characteristic equation, and these two different things. Okay, so we have to be careful. So what is the condition here? Let A be a square matrix. Yeah, so we have A be a square matrix. Then the characteristic equation of A is given as determinant of A minus lambda I equal to 0. Yeah. So see the difference. What is the difference? So here we have only polynomial. Okay, and what is the polynomial? Determinant of A minus lambda I is a polynomial. So whatever the value of this determinant, that is going to be a polynomial. But when I equate this polynomial equal to 0, then it becomes equation. Yeah, so when we equate the polynomial equal to 0, then it becomes equation. Yeah, so we have, this is going to be the equation. Okay, so this is the characteristic equation. And now we need to understand what is going to be the characteristic root. Characteristic roots, these are also called as latent roots. Okay, so how to get these roots or these latent roots? Okay, so what we can have is we have the square matrix. Okay, so what we'll be having, let A be a square matrix then the roots of characteristic equation. Okay, so this is the standard abbreviation you can use. Characteristic equation. So the roots of characteristic equation are called characteristic roots. Okay, so these are called characteristic roots. Also, they are called as latent roots. And with the more popular name, they are called as eigen values. Okay, so these roots are called as eigen values. Okay, so these are the eigen values. Okay, so is there any doubt in the definition of eigenvalue?
No, sir.
No, sir.
No, sir.
Okay, so all of you got the idea
No,
about
sir.
eigenvalue?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, that's great. So once you know about the eigenvalue, then we are able to define the eigenvector. Okay, so let us try to understand what is the eigenvector. Okay. So we got the characteristic root, latent roots. So these names, the characteristic root or latent root, are usually used in competitive examinations. So when you go for the GATE or when we go for the competitive examination, these are the words used: latent roots or characteristic roots. So eigenvalue is just the easiest form to understand, but for competitive exam, you should know the characteristic roots or latent roots are same as nothing but the eigenvalues. And now, once we have these eigenvalues, we are able to define the eigenvector. Okay, so let us try to define eigenvector. Again, these eigenvectors are also called as characteristic vector. Or these are called as latent vectors, and more popular with the name eigenvectors. Yeah, so these three things are nothing but the same. So it is eigenvector, characteristic vector, or latent vector. Okay, so how to define this characteristic vector, eigenvector, or latent vector? So in matrices, we have seen the solution of the system. Okay, Ax is equal to 0 as well as Ax is equal to B. So in the first semester, we have seen we have solved these two systems. The homogeneous system, this is called homogeneous system, this is called non-homogeneous system. So these are the system of linear equations, and we have solved the system of linear equation in first sem, and first sem we have started this matrices. Now we need to solve this system again, and then the solution is going to be eigenvector or latent vector. But what system we have? Okay, so first we need to understand. So we can say let lambda be the eigenvalue of square matrix A. Then the non-zero vector so when we denote vector, we denote it by capital letter. When we denote the element, we denote it by small letter. Okay, so let lambda be the eigenvalue of a square matrix A. Then the non-zero vector x is called eigenvector or this is also called as characteristic vector, or this is also called as latent vector. Of A corresponding to eigenvalue lambda if this x is a solution, okay, if ax is equal to lambda x, okay, or in other words, this x is a solution, okay, of a minus lambda I into x is equal to 0. So either it satisfies this equation that ax is equal to lambda x. That means if I multiply this vector x with the matrix A, then it is nothing but the scalar time vector x again. So this scalar is going to be the eigenvalue of this matrix A, and here this is going to be the matrix. So we have to be careful about the characteristic equation. So see, the characteristic equation is determinant A minus lambda is equal to 0, and this is the matrix equation A minus lambda into x is equal to 0. So here we have a matrix, there we have a determinant, and that's why we have to be very, very careful about the matrix and the determinant. So where I am going to use the matrix and where I am going to use the determinant. Okay, so we have to be careful for this. Okay, so if the non-zero vector, we are always looking for a non-zero vector, we are always looking for the non-zero solution. Okay, so this is very important. Zero is always a solution for the system. Okay, but we have to find a non-zero solution. Okay, so if I consider a matrix A, then the non-zero vector x is called the eigenvector of matrix A corresponding to the eigenvalue lambda if the lambda and x satisfies this relation. Okay, so Ax is equal to lambda x, or either way the matrix A minus lambda I into x equal to 0. So that means this x is going to be the system, the solution of this system. Okay, so x is going to be the solution of this homogeneous system of linear equations. Okay, and hence this is going to be the eigenvector. Okay, so is there any doubt in the definition of eigenvector?
No, sir.
Okay, so all of you got the definition of eigenvector?
Yes.
Yes, sir.
Okay, so that's good. See, these are very basic and very important ideas. Okay, so once you understand the characteristic equation, characteristic polynomial, eigenvalues and eigenvectors, okay, then you are able to do all the operations. Okay, so next, all the calculations. Okay, but before going to the calculations, we will try to understand what are the different relations that eigenvector and eigenvalue follow. Okay, or what are the different properties of eigenvalues. Okay, how these eigenvalues are related to the matrix. Okay, what are the entries in the matrix and how they behave, how they are related. Okay, so when we go for competitive examinations, there are several things. So they just ask the question and they are expected to answer within few seconds. Okay, so how they are going to answer it? By understanding the properties. So these properties we need to understand first, and then we'll go for the examples in detail. Okay, so what are the properties of eigenvalues, how they are related to the matrices, or by looking at the matrix, how you are able to guess what is the eigenvalues of this matrix are going to be, or how you are able to know what is the determinant of the matrix if you know what are the eigenvalues of that matrix. Okay, so these are the things which we need to understand. So any doubt up to 8?
No, sir.
No, sir.
No doubt. Okay, that's good that you don't have any doubt up to 8. So I hope you have understood the concepts. Okay, so first matrix we need to understand properly. Then we need to understand determinant properly. Okay, next we need to understand the characteristic polynomial. Then we got the idea of the characteristic equation, and now we have defined what is the eigenvalue and what are the eigenvectors. Okay, so these are the concepts that we have studied today. Okay.